G'day, my name is Jamaica Prow and this is my video project. The aim of this assignment was to select a structure within the community and apply a structural analysis method from the lectures and tutorials to investigate the key factors such as shear stress and deflections. The structure I chose to analyse is a swing set located in a local Bundoora park. The reason I chose to analyse this structure is because I pass these swings every time I take my dog for a walk, and I believe it would be interesting to investigate the structural integrity of the beam. In order to evaluate the structure, students were told to apply a triangular load to the top of the main beam by multiplying the last number of this student number by 3.33. Task 2 involves the use of this loading acting on the structure to attain the shear force and bending moment diagrams. This was followed by the calculation of the maximum slope and the deflection of the beam. Lastly, the final task of this project was to investigate the bending and shear stresses, as well as the maximum principal stress and the in-plane stresses. The first step was to draw a free body diagram of my structure and find the reaction forces at the pin support A and the roller support B. After applying the equilibrium equations, we discover that AX is equal to 0, AY is equal to 1.205 kilonewtons, and BY is equal to 3.441 kilonewtons. We then use these reaction forces and the triangular distributed load to denote the shear and bending moment functions. By taking an arbitrary length of x from the left of the beam, we are able to use similar triangles to denote y as a new load distribution in terms of x. For me, y equaled 3.3x over 3.1. Next, we are able to use the equilibrium equations again to find the functions v and m. By taking the sum of the y, we find that v is equal to 1.7205 minus 3.33 x squared over 6.2. And by taking a moment, we get m equals 1.7205x minus 1.11x cubed over 6.2. After deriving these functions, we can then graph the shear force and bending moment diagrams. The next step of the assignment was to look at the max slope and the max deflection. By using the equations EI theta equals the integral of the bending moment for the slope, and EI theta equals the double integral for the deflection, we are able to obtain two simultaneous equations. We then apply boundary conditions to both equations to find unknown values C1 and C2, and we get C2 equals 0 and C1 is equal to negative 1.9289. By subbing these two C values back into the original equations, we can obtain the new equation for slope and deflection. Using the Young's modulus for steel, which is E equals 210 GPa, and the moment of inertia of my cross section, which is 124.25 times 10 to the power of 6, we are able to sub in theta equals 0 into the slope equation to find at which position x that the max deflection occurs. This position was found to be 1.6099218 meters from the left of the beam. After finding the position for which the max deflection occurs, we can then sub that back into the deflection equation and find what the max deflection is, which is negative 3.1015 times 10 to the power of negative 5. Moving on to task 3, we can use the bending moment diagram from task 2 to find the max bending stress. To do this, we use the equation sigma equals negative my over I, where sigma is the bending stress, m is the maximum bending moment, and I is the moment of inertia. In doing this, we discover that the max bending stress is equal to negative 6.20 MPa. Next, we find the shear stress by using the shear force diagram from task 2 by taking V equals negative 3.441 kilonewtons A is equal to the area of the top semicircle, and then y bar is equal to the centroid of that semicircle to the neutral axis, and we take I, which is the moment of inertia, and B, which is the width of the cut. We are able to find that the shear stress is equal to negative 0.26 MPa. Then, by using our max bending stress as sigma x and applying sigma y and tau both equal to 0, we are able to find our maximum principal stress sigma 1, 2 equals to negative 6.2 MPa and 0 MPa. We can then use these answers in this equation to find the angle of the planes, which is equal to 0 degrees and 90 degrees. Next, we calculate the in-plane shear stress by setting tau equals to negative 0.26 MPa, which is our max shear stress, and setting sigma x and sigma y both equal to 0. And here we obtain that the max in-plane shear stress is equal to plus minus 0.26 MPa. Here we have the failure planes derived from the maximum principal stress and the in-plane shear stress. In conclusion, I did not find this task too difficult, as the lecture notes were very thorough in explaining each step of the calculation process, although following the formulas became a bit troublesome, as on numerous occasions I did forget to convert into the right units. I also found myself struggling with performing some of the calculations since my beam had a circular cross-section, while most of the examples in the lectures use rectangular cross-sections. However, I was easily able to overcome these problems and they didn't take too much toll on my assignment. The last small issue I came across was evaluating the max deflection, as it took me a long time to get the calculations correct. Overall, I believe this assignment has allowed me to practice and improve my structural analysis skills and will be useful to the real-life problems when I begin working as a civil engineer. That was my video project task, and thank you for listening.